Thank you, Terry. Good evening to you and welcome to tonight's ISEP lecture. It is my pleasure to introduce Dr. John Casti, an acclaimed author and applied mathematician. He's also a man of evidently wide-ranging curiosity and considerable scholarship, and tonight he returns home. He was born in Portland in 1943. After he completed his doctorate in mathematics from the University of California, as well as tours of duty at the RAND Corporation and the University of Arizona, he left the United States to be a researcher at the International Institute for Applied Systems Analysis in Vienna, Austria. In '92, he returned to the U.S. to join the Santa Fe Institute in New Mexico as professor and resident researcher. Also, Casti has been associated with the University of Arizona and the Technical University of Vienna. Casti's interests run the gamut from atmospheric radiative transfer to the shift of racial mixes in urban housing distribution. Recent projects focus on the role of biological metaphors for economic and other social phenomena. In his book, Paradigms Lost, he undertook the state of thought on 6 diverse topics: the origin of life on Earth, the sources of human behavior and social patterns, how we acquire knowledge, the fundamental nature of our thinking processes, the possible existence of intelligence elsewhere in the universe, and the impact of our own scrutiny on what we observe as real. His book reviewed the frontiers of several sciences and played with eternal questions such as, what is man? In the decade since that book was published, there have been dramatic shifts in these paradigms and new theories have emerged. In his latest book, The Cambridge Quintet, it is about a conversation that revolves around the possibility of creating a thinking machine. So tonight, Casti re-examines the big questions to reflect the beginning of a new century. Please welcome Dr. John Casti.
Fine. Get myself plugged in here first. Thank you very much, Maynard, for that introduction. I'd like to express my gratitude to Terry Bristol and the sponsors of this resident scholar program for the opportunity to come here tonight and talk to you. My talk is really going to be focused more in the direction tonight on the issues of limits to scientific knowledge. And in this regard, some of you might recall about 2 or 3 years ago, there was a book published here by the title, The End of Science. This was written by a fellow named John Horgan, who at the time was a writer for Scientific American magazine. And in his book, Horgan made the, I think, rather amazing claim that essentially all of the kind of great discoveries that one might make in the scientific area had already been made. That, we had discovered the laws of electromagnetism, we had discovered the double helix structure of the DNA molecule, we had discovered the general theory of relativity, and so on and so forth, and that all of the sort of the grand adventures, the grand discoveries in science were over. That essentially from here on out, the scientific enterprise was going to consist of essentially just a mopping up operation. Well, as you might imagine, this book, first of all, achieved a certain amount of notoriety and attention. A few rounds of applause from certain corners of, I think, the social sciences and the humanities communities, those who felt that science had been riding too high for too long and was due for a bit of a comeuppance. But howls of outrage from the scientific community at the actual rather shallowness of the arguments and the amazing claim that essentially everything that was out there to be discovered had more or less already been discovered. And when the book came out, this must have been in the summer of about 1996, I guess, I was actually very happy when the editors of Nature magazine, which is a British science weekly that is probably the most respected regular periodical in the scientific community. The editors of that magazine sent me an email and asked me if I would consider writing a review of this book for their magazine. And I responded by saying, yes, I'll be happy to write this review, in fact, eager to write this review, but only if you'll give me 2 full pages in your magazine to write a proper, more or less, review essay, because I felt that the issues that Horgan had raised were of considerable interest and importance, and they needed to really be somehow deconstructed, if you like, into a space that was considerably longer than a typical book review. A typical book review in Nature might have occupied like a third of a page. And to my pleasure and surprise, the editors, the book review editor of the magazine agreed, and so I set forth to not only give my opinion of Horgan's arguments, which was a rather low opinion, I might say, but also at the same time, and much more importantly actually, to raise a whole spectrum of issues in this essay to the effect of that science was certainly very far from being over. And I might mention that happily for both John Horgan and myself, when this review was published, the very next day, Horgan and I each received emails from the Nobel Foundation in Stockholm saying that we view with great interest this debate about the beginnings and the ends and the end of science, and would each of you be willing to come to Stockholm at the time of the Nobel Prize ceremonies, second week of December, and publicly debate this issue about the end of science. Well, of course, who could resist such an invitation? And neither Horgan nor I resisted, and we dutifully trotted off to Stockholm in the second week of December and fought it out, metaphorically speaking, in fact, in a theater not very much different than this one in Stockholm. I might say that it was very unclear, of course. There were no votes taken at the end of that debate as to the winners or losers, but John Horgan and I actually became rather good acquaintances and good friends, and we shared some pretty pleasant experiences in Stockholm during that week. So we were only intellectual rivals, not personal ones. It doesn't always happen that way in science. One of the points that I raised in my Nature essay was the fact that Horgan had ignored, in my opinion, a whole spectrum of important unsolved problems in science, and that I thought it was at least worth listing some of them in the essay. And these are some of my favorites. I'll put them up here for you on this overhead. Many of you may remember, and Maynard Orme was very kind to mention a moment ago, that in one of my books, Paradigms Lost, that book deals, each chapter addresses one big unsolved problem in modern science and gives a kind of an account of who holds what positions and why they held them and how they came to this view and so on and so forth. And so I thought that since, as far as I could tell, at the time of Horgan's book, and today as well for that matter, not a single one of these problems is anywhere near being satisfactorily answered, that this list of big problems, and I'm sure everyone here in the audience could greatly expand upon this list of problems would certainly serve as a good antidote to the idea that science is anywhere near coming to its end. And so let me show you this list again. There we are. Okay. So, big questions of modern science, and these are the ones that are dealt with in Paradigms Lost. How did life on Earth get started? The origin of life. Second problem. Are human social behaviors, behavioral patterns, Are they primarily dictated by our genes, or are they do they arise from cultural phenomena? This essentially is the problem of sociobiology. Third big problem, how do we acquire language? What separates humans from the animals, by and large, is our linguistic capabilities. One of the major distinguishing features between human beings and animals. Well, how do we get that capability? How do we actually learn our native language? Problem of language acquisition. Is it something somehow built into the human brain? Is there a special kind of language organ that is part of our natural birthright? Or is it something that we just learn in the same way that we learn to ride a bicycle or learn to tie our shoes? The problem of thinking machines, artificial intelligence. Can we build a machine, and I'll use the term machine in a general sense, that's capable of duplicating human thought processes? Duplicating human thought processes. Can we build a machine that thinks like a man or a woman? No one knows. We certainly can build machines that do some cognitive activities like humans, or at least perform as well as humans. They may not actually carry out the functions in the same way. Chess playing is a good example. We now have computer programs that play a better game of chess than the world champion, Garry Kasparov. So the answer to that question is, well, maybe if you restrict the domain of activity, but the real question is, can we build a machine that duplicates the whole spectrum of human cognitive capabilities? Problem of extraterrestrial intelligence. Are there intelligent beings in our galaxy with which we can be in meaningful communication? Well, we've never met one yet. UFO people notwithstanding, there's not any solid evidence that such extraterrestrial intelligences do exist, but there are a lot of reasons for believing that they probably do. But it's an unsolved problem in science. Finally, we have the problem of quantum reality. How real is the real world? And how do we know about the nature of the physical world around us when we make observations? How do we interpret, how do we understand these observations in order to give us a picture of the way the world really is, as opposed to the way we might think or wish that the world was? Quantum theory is a big step in the direction of addressing that kind of a question, but it's still an unsolved problem in modern science. So here are at least 6 counterexamples to John Horgan's argument about the end of science. And as I said earlier, I'm sure that everyone in this audience could add several more problems to this list. Just put down your favorite. These happen to be my favorites, but there are many others that could be added to this list. So I think that there's a lot of reasons to believe that Horgan's argument about the end of science is vastly premature, to say the least, and probably just plain wrong. Nevertheless, despite the sort of fuzzy-headedness of the arguments presented in that book, in fact, there were some arguments, or at least the germ of an argument in that book that I felt had a considerable amount of merit and was in some sense struggling to emerge from all of the hype and ad hominem kinds of discussions that Horgan entered into in his book. And that argument, or question is really, it's not an argument, it was a question, is an important one. And it bears actually on all of the questions that I've just put on this overhead that I've just shown you. And that's the question, not is science at an end, but are there limits to what we can know about the world around us by using the methods and tools and approaches of science? In other words, Horgan essentially is saying, yes, there are limits, and we're already there right now. My question is really more in the direction to say, well, first of all, are there any limits at all? And if there are limits, what is the nature of those limits? And this is the issue that I really want to discuss with you tonight. Now, one way of rephrasing that question might be to say, well, is the real world too complex for us? This is a version of it that we're very fond of in Santa Fe, because Santa Fe Institute is a place devoted to the study of complexity, the sciences of complexity, if you like. We're interested in what we call complex adaptive systems, wherever you find them, and you find a lot of them in the real world. So the issue that Horgan does not address, but which his book certainly, at least implicitly, calls attention to, is, are there limits to our ability to know about the world by using the tools and methods of science? Now, in order to sort of effectively talk about that question, you have to be a lot more specific about what do you mean by a limit, what do you mean by the scientific knowledge, and how do you actually operationally define these terms to actually try and answer that question. Now, in a kind of trivial sense, one can say, yes, obviously there are limits to what it is that we can know about the world by the methods of science or any other methods. There are lots of, call them practical limits, questions that we might be able to answer but would require a vast expenditure of money to build certain kinds of, let's say, giant particle accelerators, or might require enormous amounts of time and engineering virtuosity to build devices to go to the other side of the galaxy. Or there might be limits of a political or a social type. You know, limits, moral limits, for instance, against, for example, cloning human beings. Or political constraints about the kinds of investigations that are sort of politically correct. So we can all think, I think, of a lot of limits on what it is that we might be able to know by using the tools of science, limits of this kind. Call them practical limits. Those aren't the kind of limits that I'm interested in. What's of much greater intellectual interest is the question, are there logical limits? There are logical limits to what we can know by using the methods of science. And one of the reasons that this question comes up is that we know in mathematics is just filled with these kinds of undecidable questions. That you can ask many different types of questions about numbers or mathematical objects, and you can prove that using the traditional, conventional methods of mathematical reasoning and argumentation, that you will never be able to know the answer to this question. These questions are logically undecidable. And in fact, the situation is a little bit worse than this. One can actually show that if you would envision the set of all possible statements that you might make about numbers, you know, that the sum of two even numbers is an odd number, or the square of a number is positive. Some of these statements we can prove are true, some we can prove are false. But with probability 1, if you just sort of randomly pick out a statement about numbers, we can also show that that statement will be undecidable. You can neither prove it nor disprove it. It remains in a kind of limbo forever. So the world of mathematics is completely riddled with unanswerable kinds of questions. And in fact, when you look at it from this point of view, you think it's slightly miraculous that we can ever know anything in mathematics with any certainty, that we can ever prove anything. And this is a good argument, in my opinion, for the fact that mathematicians, they don't just sort of randomly pick out statements and try and prove them or disprove them. They use intuition, and they use understanding and feeling for relationships to sort of navigate around in this territory that's filled with sandbars and reefs and all sorts of nasty things, to find those propositions and to focus their attention on those kinds of things that actually can be proved or disproved. But what about outside of mathematics? What about in the worlds of physics or biology or economics or train science or engineering? Do we have similar kinds of questions in these areas? Questions that actually have very simple statements, for example, but for which we can produce a convincing argument that the methods of science will never allow us to come to a conclusion, a definite answer to that question. Well, I'm going to come to that in just a moment. First, let me go back to this issue that I said a moment ago about making more specific what do we mean by knowledge, what do we mean by scientific knowledge, and what do we mean by a limit. Now, I've already told you what I mean by a limit. I mean a logical limit, not a practical limit. But what do I mean by knowledge? Well, for the purposes of our discussion tonight, let me just be very sort of simple-minded in this regard, and I'll say that you acquire knowledge when you provide an answer to a question. Knowledge is the answer to a question that you previously didn't know the answer to. Now, of course, this requires a certain kind of, call it social consensus, that we can agree that a particular answer really is the answer to that question, whatever the question may be. This is a kind of information theoretic view of knowledge, that you acquire knowledge when you provide an answer to a question. Now, what about scientific knowledge? Does scientific knowledge, the kinds of knowledge that we acquire by using the methods and tools of science, does scientific knowledge differ in any important way from just knowledge in general? Now, that means when we use the methods of science, do we produce the answer to a question in a different way than by answering the question using intuition or experience or personal opinion or whatever? Well, my claim is yes, indeed, you do produce the answer in a very different way. Essentially, the scientific way of answering a question is to produce an algorithm or a formula or a procedure, a set of rules, if you like, that the question goes in one end and you invoke the rules or run the program and the answer comes out the other end. That's the scientific way of answering a question. And let me show you, here's a good example of a scientific rule. This is a picture of a famous experiment, thought experiment in quantum mechanics called the Schrodinger cat experiment. And there's something in quantum theory called the Schrodinger Equation, which describes this situation. And the Schrodinger Equation is an algorithm for answering a particular question about this situation. So let me explain it to you. What we have here is this enclosed box, A, and inside this box is a small piece of, let's say, some radioactive element that at any given moment might emit a particle or not emit a particle. Okay? spontaneously emit a particle. Now, if at a given moment that piece of radium, say, emits a particle, that fact is detected by this detecting device, which then transmits that information to this hammering device, which then will crash down onto this flask of acid, which will then release a poisonous gas in this box, and this poor cat will expire. It will lose one of its last of its 9 lives, let's say. Okay, that's what happens if a particle gets emitted from this piece of radium. On the other hand, if no particle is emitted, the cat lives on for one more tick of the clock. Okay. Now, as an observer here on the outside, here's Schrodinger standing on the outside of this box. He can't see what's going on inside. And he might ask, okay, at this moment in time, is that cat alive or is the cat dead? Okay. Now, from the standpoint of traditional, let's say classical, everyday logic, you might say, well, even if you can't look inside that box, the cat is definitely at any moment either dead or alive. All right. There's not an in-between kind of state. You're either alive or you're not. Now, quantum theory says something quite different. Quantum theory says that there is an object called the Schrodinger Equation, an algorithm, if you like, that describes a kind of wave of probability for this situation. And all that you can say from the outside, without looking into the box, is that at any given moment, there's a certain likelihood that the cat is alive, and another likelihood that it's dead. Okay? In some sense, it's partly alive and partly dead. And quantum theory further goes on to say, if you open up the box and look in, that all of a sudden this wave of probability collapses into a single point that is either at the point alive, definitely alive, or definitely dead. So that there's something very mysterious about the act of looking. That looking, that observing, causes this wave to collapse to a single point. But before you look, all you can say is that the cat is partly alive and partly dead. All right. Now, from the standpoint of the question of a scientific rule for answering a question and producing scientific knowledge, the Schrodinger equation is an excellent example of a scientific rule. And here are some of the, down here at the bottom, some of the properties that characterize a scientific rule, and which tend to distinguish a scientific rule from just any old general set of rules, like the 10 Commandments or something like that. It's a set of rules too, but I don't think any of us here would in any way regard them as necessarily being scientific. Well, a scientific rule has certain kinds of properties. First of all, it's explicit. It's very clear and unambiguous as to what the rule actually says and how to use the rule. Now, you might require a very well-equipped laboratory and years of training to actually understand that rule, but once you have that training and that equipment, you can understand the rule clearly and use it. Furthermore, the rule tends to be reliable. It's a rule that has reported reliably in the past, if you like. So we have some confidence that it works. Third characteristic, it's a publicly available rule. Publicly available in the sense that it doesn't require any private interpretation to understand what the rule says, and the rule is made available to all comers. As I said, you might have to have a very well-equipped laboratory or some other kind of specialized knowledge to use the rule, but it's freely available to anyone who wants to try and use it. It's not kept in a secret way. Another characteristic is scientific rules tend to be objective. Now, I've put objective here into quotes to indicate that I do not mean that it's objective necessarily in the sense that it exists completely independent of human investigators. I don't have quite such a Platonic view of the world. Nevertheless, I mean that it's objective in the sense that the rule itself is independent of the biases of a particular researcher or investigator. So, for example, if you think about Newton's inverse square law of gravitation, it's an inverse square law, and the exponent in that law is 2, and that exponent doesn't change if the investigator happens to belong to the Democratic Party as opposed to the Republican Party, or if the status of the investigator's bank account does not influence what the nature of the rule is. So this is what I mean when I say that it's objective in the sense that it's independent of the biases of any particular investigator. Okay, so now these are some of the kinds of properties that tend to characterize scientific rules, but there's also another feature that separates scientific rules from the pretenders, and that's the way that you actually arrive at the rule. How do you actually get to the rule? Well, in the areas of science, we have something called the scientific method. And the scientific method helps us generate scientific rules. The scientific method is typically you have some observations, you make some hypotheses about a kind of a theory that would account for these observations. You go into a laboratory to do some experiments to test your hypotheses, and as a result of those experiments you may modify the hypotheses and create some new experiments to perform, and you keep going around in this loop. And what you hope is that as you keep going around, you start eventually converge to something. And that something that you converge to is what we call the scientific rule. That's how you arrive at the rules or the theories that we call scientific. So a scientific rule then is a rule that has certain collection of properties and is generated by a certain kind of procedure, the scientific method. And this helps separate something like the Schrodinger Equation from the Ten Commandments. But I might mention that the notion of what constitutes a scientific rule is not completely time independent. Take, for example, the kinds of rules that you see in astrology books. Okay, I'll give you a simple example. A typical astrological rule might be the position, let's say in your birth chart, of the planet Jupiter in the second house says that you should have good financial fortunes during the course of your life. Okay, that's a typical kind of astrological rule. The planet Jupiter is supposed to represent forces of expansion. The second house typically is supposed to represent the kinds of resources that come to you from your own efforts, usually financial resources. So if you have the planet of expansion sitting in the second house, you should have a happy financial life. Right? That's a kind of typical astrological rule. Now, in today's world, we certainly would not consider the rule Jupiter in the second house means financial fortune. We wouldn't consider it to be in any way scientific. Nevertheless, if I was giving this talk, say, 500 years ago, or at the University of Bologna, that particular rule would have been the height of scientific responsibility, or scientific respectability, because astrology in those days was considered to be part of the scientific background of any educated person. And Jupiter in the second house was a rule that was right at the center of good science. Okay. So the point here is that what does or does not constitute a scientific rule can be a time-dependent phenomena, and sort of one generation's magic is the next generation's science. So you have to bear that factor in mind. But roughly speaking, a scientific rule, just think of it as a computer program. That's close enough for the discussion that we need to have tonight. And it's the rules that we use to answer questions. Now, one of the important aspects of this view of the practice of science is that these rules that we use, like the Schrodinger equation, they tend to be expressed in mathematical formulations. They tend to be expressed as mathematical formulas or theories. And I said earlier that in the world of mathematics, we have all sorts of undecidable, unanswerable questions. But we're not interested here in the world of mathematics. We're interested in the world of real things and real people. These aren't the same worlds at all. And this is a factor that one has to keep very carefully in mind when you start looking at this question, limits to scientific knowledge. Because it's very easy to slip into a kind of abuse of language and start identifying the map with the territory, to start identifying the mathematical formulas with the actual phenomena itself that these formulas are supposed to represent. So here's a little picture just to fix that fact in your mind. This is a famous picture from the Belgian painter Magritte. And underneath here, this says, "This is not a pipe," says it in French. And it's to emphasize the point that a picture of a pipe is not the same thing as a pipe. And I'll say the same thing down here. Here is the mathematical expression for gravitating bodies like the planets moving around the sun. Well, this is not a pipe, and this mathematical formulation, this is not the solar system. This is a mathematical picture of the solar system. And so if you have some questions about the real world of real planets moving around the real sun, and you translate that question into this world of mathematics, all of a sudden you've left the real world and you're doing mathematics. You're in a world where we know there are lots of undecidable questions. But that's not the world that you're asking the question about. Okay, I'm going to come back to that point later, but it's very important to remember a mathematical model of a situation and the situation itself are not at all the same thing. The mathematical picture always contains simplifications and abstractions, and things are left out of the real picture. And so if you make an argument in the world of mathematics that a certain question is unanswerable, you have to be able to produce a convincing line of reasoning to say why all the things that you left out don't matter. Okay. Now let me just show you 2 or 3 problems from the so-called real world that I'm not making any claims that these problems are necessarily unanswerable. We don't know the answers to them today. They might be good candidates for questions that are beyond the bounds of science to ever answer. I'm not going to make that claim. I'm not John Horgan. I'm John Casti. But nevertheless, they're representative of the kinds of questions that might ultimately turn out to be beyond the bounds of science to effectively address. So the first one I'm going to show you is a problem from physics, a famous problem from physics, the so-called N-body problem. And what this problem says is that suppose you have N bodies like the planets moving around the sun. So you have N bodies in gravitational motion around each other. And the N-body problem says, is there some time in the future, some finite time in the future, when either you will have a collision, 2 of these bodies will collide, or one of these bodies will attain such a high velocity that it will just escape. It'll fly off into outer space. Okay, that's the question. That's the problem of the N-body. And one way of rephrasing it in terms of the real solar system is to say, is the solar system stable? Or will there come some time in the future where two of the planets will crash into each other, or one of them will just disappear completely from the system? All right. Now, the answer to that question, if you have only two bodies, like the Earth and the Moon, if you have only two bodies, then we know the answer to that question. We can explicitly work it out in very definite terms. But as soon as you have three or more bodies gravitating around each other, then we don't know the answer. And you might think at first glance, you might say, well, if we know how to solve the two-body problem, then we can take this three-body problem, the sun, the earth, and the moon, and we can solve the problem for the sun and the earth, for the earth and the moon, and the sun and the moon, and somehow we can glue these solutions together into a solution for the three-body problem. Well, it doesn't work that way. You can't glue these solutions together. That by tearing the system apart into three two-body problems, you've done irretrievable damage to the actual problem, and it can't be repaired. You cannot put it back together again, like Humpty Dumpty. Now, for a long time, people they still don't know the answer to the n-body problem, but a few years ago, a mathematician at Northwestern University named Jeff Shaw constructed this example that I've drawn here for you of five-body. It's a five-body problem, 5 tennis balls essentially. There are two two-body problems where these, like a binary star system, revolving around each other in a vertical plane, and the fifth body moves back and forth between these two-body systems. And every time this ball goes through this system, it goes out here and then it's drawn back by gravitational forces and goes back again, and then back, and then back, and it gains more energy each time, like a slingshot effect. And so if you tell me some velocity, I can, no matter how big, I can tell you some finite time in the future when that tennis ball is going to have a velocity greater than the number you name. So this is an example of a five-body system that is unstable. Eventually, you might say that that fifth tennis ball, it will eventually fly off out of the system. So now, here is a example of a case where, if you've thought of this as a solar system, of a case where the solar system is unstable. One of the planets will eventually leave the system. Now, nobody would make any claim that there's any planetary systems anywhere in the universe that look at all like this one. I mean, this is a mathematical idealization. You have these two-body systems lined up parallel to each other in planar motion, and another body that goes back and forth between them. No natural systems look like that at all. So this is a mathematical concoction, if you like, just to show that it's theoretically possible that you could have an unstable system. But what about in the real physical world? What about in the world outside of mathematical solar systems? Well, nobody really knows. Nobody knows. But we at least know in the mathematical picture of a solar system that you could create something that would be unstable. Now, let me show you an example of a problem in biology that's also, at the moment, unsolved. This is a famous problem in molecular biology called the protein folding problem. Now, in this world, proteins, which are the real doers of the body, I mean, the stuff that really makes everything happen in your body are the proteins. And all the known proteins, at least in living things on Earth, are like, they're formed by strings of amino acids. And there are 20 different amino acids that living things on Earth use. And every protein is like a necklace formed of strings of these 20 amino acids just strung together like beads on a necklace. And in your DNA, the instructions for building these proteins are coded in your DNA, and when it's time for the cell to build these proteins, the ribosomes move along the DNA strand and they assemble these beads one at a time until you have the so-called primary structure of the protein, which is just a linear string of all these beads, and then it stops. And almost immediately then, after the assembly is over, this string folds up into some very specific three-dimensional configuration. And that geometry, that three-dimensional geometry, is what determines how the protein actually works, what function it performs. So it's very important to know what the three-dimensional geometry of the protein actually is. Now, this picture that I've shown you here is for a very, very simple protein called cytochrome C. It's maybe one of the simplest of all proteins. It has only about 100, maybe 110 amino acids. And here they are, sort of strung together here on the left. This is the so-called primary structure of that protein. When it's all strung together, then this protein will fold up into this three-dimensional configuration that I've shown here. And it's this configuration that determines how cytochrome C actually works, what it does. Now, the protein folding problem in the world of mathematics, let's say, is if I give you this string, tell you what all these amino acids are, can you compute what the three-dimensional geometry will be by using minimal energy arguments and so on? Can you calculate what kind of configuration this string will fold up into? Well, if you use normal computational methods, even on supercomputers, you can actually show that this problem is what's called NP-complete. It's a hard computational problem. And it might take somewhat in excess of the age of the universe on the best supercomputers today to even fold up mathematically this simple protein. But if you go into the biology lab and string these 110 amino acids together and watch cytochrome C form, somehow it folds up into the right configuration in about 1 second. Okay, 1 second. So somehow nature is carrying out a computation, if you like, in 1 second that we don't know how to do in the age of the universe with the kind of computing capabilities that we currently have. And since the scientific answer to a question is essentially a computer program, that program has to run somehow in some kind of a computational device, we might legitimately ask, perhaps the protein folding problem is beyond the bounds of the science, certainly beyond the bounds of the science of today, to give a good answer to how does this string, what kind of geometry will it fold up into? Okay. Maybe we're just not clever enough. I mean, I don't want to make a claim that necessarily this is forever undecidable, but at the moment, nobody knows how to effectively solve this problem. The best way to solve it is you string the proteins together, the real amino acids together, and just watch what it folds up into. The problem with doing that is that most proteins have a lot more than 110 amino acids, and they can be very complicated, and people want to develop new kinds of proteins. Drug companies and medical investigators would like to experiment with new types of proteins that might perform functions that would be very helpful to us. But without knowing what kind of geometry, we know the kind of geometry we would like to have to perform a certain function, you might say then, what kind of string of amino acids do you have to put together in order to get that geometry? Kind of an inverse problem. And that's even harder than the original problem. So this is a very, very good candidate for a problem that's scientifically hard, if not impossible, to solve. Now, my third example for you is from the area of economics. And it involves financial markets. And the question that I will pose to you is, are financial markets efficient? There's something in the world of academic finance called the efficient market hypothesis, which is a kind of pillar of the academic theory of finance. And what the efficient market hypothesis comes in many different flavors and colors, but roughly speaking, what it says is that whatever information may be available that influences the price movement of a particular security, say a stock, that when that information comes publicly available, it's instantly assimilated by the market and built into the price of the stock. So that there is no delay, there's instant data processing, instant assimilation of all information. So the current price of the stock contains every bit of information that's known that could possibly influence that security. That's what you mean by market efficiency, if you like. Now, when I state it in such dramatic terms, it sounds like it's a pretty fishy kind of proposition. And in fact, there are lots of people down on Wall Street who've made very good livings laughing for years at the efficient market hypothesis. So one might ask, well, if it really is just an idealization, how much of an idealization is it? And under what circumstances might the efficient market hypothesis be even approximately true for real financial markets? Well, another way of talking about it is to say that price movements are essentially random. Because you can make the argument to say, well, if it's the information that comes into the market that determines the movement of prices, and information itself only appears in a random way, therefore the price movements themselves should be random. That's another version of efficient market theory. So here's a little picture that I won't explain to you the technical aspects of this graph. I only want to say that this is a graph that has to do with the price history of something called the Standard & Poor's 500 index of the American stock markets. And these little boxes here are the price computed in a certain way, that index. And this line right here, if the efficient market hypothesis were true, strictly speaking true, all of these boxes should lie right straight along that line. And what you can see is that they're very far away from that line. About as far away from being on that line as you can possibly get. So from a viewpoint of a mathematical model of a stock market, which assumes the efficient market hypothesis is true, things should be along this line. Prices should be random. But in the real world of finance, these boxes represent the real price movements. So the question that might be unanswerable by scientific methods, scientific argumentation, is to what degree can we place any confidence in market efficiency? Are there any circumstances under which prices might move right along that line and not along something very far away from that line? Okay, so now I've given you three actually big questions outside of the world of mathematics, the NBody problem, the protein folding problem, and the market efficiency problem. Each of them has a mathematical representation that we can use to prove or say certain things about the mathematical picture of that problem. But what we're interested in is the real world version of that problem, not the mathematical picture. So if you want to make an argument to say that one or another of those questions is, in the real world, is beyond the bounds of science, then you're really perched on the horns of a dilemma, a very difficult dilemma. Because you can take the real world problem and you can translate it into the world of mathematics, and then you have a mathematical formulation of an idealized version of that problem. You can use then the machinery of mathematics to try and decide whether the question is undecidable in this idealized version. If it is, then you have the burden of saying, well, is my mathematical picture accurate enough that the mathematical question that's undecidable matches faithfully the real world question? In that case, if you can make that argument, then you can say, yes, science cannot answer this question. But it relies then on making a convincing argument that this mathematical model is of such high fidelity that the undecidable mathematical question implies the undecidability of the corresponding question in the real world. Okay, that's one horn of the dilemma. How do you make that model and the real world congruent enough that you can believe that the mathematical arguments apply to the real situation? The other horn of the dilemma is to say, well, let's forget about mathematics entirely. Don't take this problem and translate it into mathematical terms. You say, why do we translate it into the mathematical world at all? Well, the main reason, the only really good reason for translating into the world of mathematics is that's the only world where you have the notion of an idea of a proof. In mathematics, you can actually prove things. You have a logical framework and you have the tools of logical inference and deduction and so on, where you can give airtight logical proofs. Okay, and we like certain levels of certainty, and mathematics is a place where you can get proofs. When you're outside of the world of mathematics, you have no notion of proof. So if you don't translate your problem, or your question about protein folding or the movement of planets or whatever, if you don't translate it or paint a mathematical picture of it, but just stay in the real world and the world of natural things, in that world there is no notion of proof. So if you want to have some confidence in saying this question is beyond the bounds of scientific argumentation, scientific analysis, then you have to somehow create something that serves as a substitute in the real world for the notion of proof in the world of mathematics. So in either case, you have a difficult task in front of you. Either create something in the real world that serves the same purpose as proof in the mathematical world, or show that the mathematical picture that you've painted of this real world situation is of such fidelity that the mathematical model and the real world situation are completely congruent to each other, so that what you learn in the world of mathematics applies in the world of actual phenomena. So so here's a very short overhead that gives that one horn of that dilemma. If you stay in the physical world, the world of economic processes and planetary systems and real proteins, what is proof? What is proof? Well, I don't know what proof is in that world. But I do know that in the mathematical universe, if you can ask, how do you arrive at the idea of undecidable propositions? How do you know that certain kinds of statements about numbers will never be answerable that there is no chain of logical reasoning that will ever take you to the answer to these questions? Well, the way that you know that is by something in mathematics called Gödel's theorem. Let me show you a picture of it. Gödel's incompleteness theorem. And here's a little diagram that gives the general idea. Look at the top half of this picture. Suppose that you have this square, and that initially all the points in that square are colored gray. And suppose that every single point in that square represents some statement that you can make about numbers. Like I said earlier, you can make the statement, the sum of two even numbers is an even number. Well, that's a true statement about numbers, and we can actually prove that it's true. So you go to that point, and since we can prove that it's true, we color it white. Now, there are other statements about numbers that we can make, like the square of a number is negative. We know that statement is false, and we can prove that it's false. So we go to that point and color it black. Okay. What Gödel's results said is that you can't get rid of all the gray. That there always must necessarily exist a point in that square like this one, that I've labeled here G in Gödel's honor, that can never be decided whether it should be white or black. It has to remain gray. Now, this is a result in logic, and it relies on the fact that the mechanisms that we use to create proofs in mathematics, what are called formal logical systems, that they are consistent. And all that means is that it's not possible in this mechanism to take a statement and simultaneously prove that the statement is true and prove that it's false. You can't prove the statement and its negation both. If one of them is provable, then the other one must necessarily be false. And that's the idea of consistency, logical consistency. You can't simultaneously hold two completely mutually contradictory views. Now, of course, we know in our brains we do that all the time. But in mathematical systems, this is very bad news, because if you have a system, a logical system that's inconsistent, any statement you make is then a theorem. Anything is provable in such a setup. And if anything is provable, then the whole setup is completely useless. It doesn't distinguish between true statements or false statements. Okay, so logical consistency is a kind of bare bones minimum requirement for any deductive system in mathematics. And what Gödel's theorem says is if you have a system that's logically consistent, then it must necessarily be incomplete. Incomplete in the sense that there are some statements that you can make that can never be shown to be theorems or not theorems of that system. They're in the realm of the gray forever. It happens that theorem, which seems rather esoteric in some sense from a logical point of view, is completely equivalent to a different result in the area of computing, which to my own eye anyway is a lot more easy to understand. And that's something called the halting theorem in theory of computation. And what it says is that suppose that I give you a computer program, and some data that this program is going to operate on. And I ask, when this program starts running and operating on this data, will it ever stop? Because the stopping criteria for most programs are something like, if such and such a quantity turns up in the course of the computation, then stop, otherwise keep computing. But in general, you don't know ahead of time whether or not that stopping criteria will ever be satisfied, whether that quantity will ever appear during the course of the computation. So the halting problem says, the question is, can I construct a computer program into which I can feed every other computer program, and that this sort of master program will give me the answer, yes, this program will stop after a finite number of steps, or no, it will keep running forever. So does there exist a single program that will decide the stopping or not stopping of every other program? Okay. Now that seems like a fairly practical kind of thing, that it would be very nice to know before you start off on a computation whether or not the program is ever going to stop running. And I think any of us who have ever done any computer programming will know that it's very easy to get into infinite loops where the program just sort of goes on forever. Sometimes it's by accident, sometimes it's just part of the problem. And the answer to that question is something called the halting theorem. And the answer is no, there cannot ever exist such a master program that will decide the stopping or non-stopping of every other program. No such thing can exist. And it's completely equivalent to this theorem of Gödel's. It's a kind of computer science version of Gödel's theorem. Now, I said that if you want to stay in the realm of the physical universe only, you have to put something in the notion, in place of the idea of a proof. And that means that you have to basically produce some kind of physical analogs, if you like, of the idea of consistency and completeness. I told you in logic, consistency means that you can't have two mutually contradictory things be simultaneously true. And completeness means that every statement that you possibly can make is decidable. It's either a theorem or its negation is a theorem. And it's either a theorem, it's either true or false. It's not in between. Now, what could we say about the physical world that would serve as substitutes for the ideas of consistency and completeness? Well, let me give you my conjecture in that respect. I would claim that the idea of consistency in mathematics, the fact that you can't hold two mutually contradictory positions simultaneously, is its counterpart in the physical world is that there are no true paradoxes in nature. That water does not run uphill and downhill simultaneously. Or if you toss a ball, it doesn't go up and down at the same time. And that any kind of paradoxes that you see or think that you see in nature, that further information will show that that paradox is not a paradox at all. That nature hates, just like I think nature hates infinities, nature also hates paradoxes. That nature is actually consistent. Now, the notion of completeness is a somewhat more delicate one. Completeness in mathematics, remember, says that every statement that you make can either be proved or disproved. That means that there's a logical chain of arguments that proceed from some axiom and that eventually bottoms out at the statement that you want to prove, or it bottoms out at its negation. Now, I would offer for your attention the idea that the physical counterpart of that notion of completeness is that every physical event that takes place has a cause. that things in nature don't just happen, that there is a causal chain of events that you can trace back, maybe even trace back to the Big Bang or the beginning of the universe, that will explain whatever it is that you happen to see. That things don't just sort of spontaneously take place, apropos of nothing. So those are my candidates for the notions of consistency and completeness in the physical world. And if they are correct, then the idea, the question, what is proof? Proof in mathematics is just a chain of logical arguments, implications, if you like, that truth or proof in the real world, the world of physical things, is just a chain of causal statements. The A caused B, which caused C, which caused C, and so on, like that picture that I showed you of Schrodinger's cat, that sort of Rube Goldberg kind of device, that the radium emitting caused the hammering device to crash down on the flask, which then caused the poisonous gas to come out, which caused the cat to die. Okay, and that's a kind of causal chain of events. All right, so my answer then, the question that we started with was, what are the limits to scientific knowledge, or are there limits to scientific knowledge? My tentative answer is that unlike the world of mathematics, in which we know there are zillions of limits, logical limits, questions that we will never know the answer to by following any logical chain of deduction, I would claim that in the real world, or conjecture is probably better, that the real world is consistent and complete. See, all of these undecidable things in mathematics are a consequence of Gödel's theorem. Gödel's theorem says you cannot have a logical system that is both consistent and complete. If you want one, you can't have the other. So if it's consistent, then it has to be incomplete. And that's where you get all of these undecidable statements. My feeling is that the real world is a lot more benign than the world of mathematics, and that it is both consistent, there are no paradoxes, and it's also complete, that every event that takes place in the real world has a causal chain. Now, if this is correct, then there are no logical limits to science, because the production of a scientific answer to a question is essentially the production of a computer program that answers that question, a computation, which itself is a logical system. So if the real world is both consistent and complete, then you have no logical limits to science. And Horgan is wrong. He's wrong anyway, but he's especially wrong in this case. Okay, so anyway, I hope that this has given you at least a little bit of a feel for some of the kinds of things that one worries about when you start going off into this gray zone where sort of science becomes philosophical and philosophy becomes scientific. This line of investigation on limits to scientific knowledge is something that's actually relatively new. I can say to you that if you want to see more of these arguments in greater detail, but not so much detail that it's painful, I wrote an article about this in Scientific American magazine about 2 years ago now. I think it was in the October 1996 issue of Scientific American, and you can find a lot more information in that article. So I'll thank you now for your attention, and I think we'll have some questions. Okay, thanks. That's good.
Feel free to leave. Can everyone hear me? Feel free to leave if you need to go. I won't be offended. I don't think Dr. Casti will either. So John, you grew up in Northeast Portland, and now you've traveled the whole world, and what's it like to return?
Well, it's a little unsettling, actually. It's sort of strange to return back to an environment that in some ways is so completely familiar, you know, to revisit your past. But in another direction, for example, I went out today to Beaverton High School to give a talk. And at one time in my past, I actually lived and worked in Beaverton. I worked at Tektronix. And this whole area was completely unrecognizable to me. I mean, I had no idea where I was. There had been so much massive development in this area that I felt like Rip Van Winkle. You know, I'd been asleep for 100 years and had come back to some completely new universe. But last night I'd gone out to my old neighborhood where I grew up in Northeast Portland, and it was completely unchanged. There wasn't a single thing that was different from my childhood. So it's a little bit disturbing seeing this big dramatic differences in these different parts of this same area.
Wow. And you're going off to Japan tomorrow,
yeah,
I guess?
Yeah.
So I know there's one human interest thing I have to get out of the way too. You're getting married in a few weeks, I hear, and
in January.
I hear your ceremony is going to be somewhat interesting. You want to share that with the audience?
The marriage? Well, it's not so much the marriage. Well, the marriage might be a little interesting, but it's the place where it's taking place, up north of the Arctic Circle in Lapland in the middle of January. And I can't even begin. It would be a whole another hour lecture to describe the circumstances that brought that about. But I'm marrying a woman from South Africa, and I'm from Santa Fe, and we're getting married at a place that's about as far away from either of those places as you can get and still stay on the same planet. So maybe that's part of the reason.
Good. Well, congratulations.
Thanks.
In a lot of the visits to the schools and also to Intel, which I'd like to ask you about that in a little bit, but you talked about your work with simulations at Santa Fe, and
yeah.
What are the implications of being able to simulate such massive problems, and particularly social and behavioral problems? What are the impacts on society going to be of those simulations?
Well, I'm very interested in large-scale simulation now because I regard the development of computer technology has now reached the point where one can realistically think about building electronic copies in your computer of all sorts of systems of the real world that previously were beyond the bounds of experimentation. You know, financial markets and road traffic networks and evolutionary ecosystems and so on. In the past, if you wanted to create some kind of a scientific theory of these systems, you were completely stymied by the fact that it was impossible to do experiments with them. You know, the scientific method I mentioned earlier, one of the crucial steps is that you have to be able to have a laboratory where you can go in and do controlled, repeatable scientific experiments in order to test hypotheses. And if you have some, let's say, theory of finance, you can't go down to Wall Street and ask them to change the rules so that you can check up on your theory today. It's just not practical. And even if you could get them to do that, you could never repeat the experiment. You could never set things back and do the experiment a second time. Now, for the first time in history, we have the opportunity, because of the computing technology, to actually build faithful electronic copies of these systems inside our computers and do the experiments that we need to do with these electronic copies, and to do the experiments there that we cannot do in the wild.
And one particular project that I think we might all be interested in, because for the last 20 years, Portland's really had a very strong sort of urban planning system and land use, is you in the most sophisticated supercomputer, and I guess in the world at Los Alamos, you modeled the city of Albuquerque. You put every person and home and where they worked and everything. Can you tell us a little bit about that?
Yeah, well, I mean, it was a very extensive and fine-grained, high-resolution simulation. The idea was to take a major metropolitan area. It happened to be, we chose Albuquerque, New Mexico, because it was nearby and we had a lot of data and for a lot of other reasons as kind of the prototype, and build into the computers. This work was done at the Los Alamos National Laboratory. And build into those computers the entire road transport system network of that town. You know, not just the freeways and the main streets, but even the back alleys and residential streets and so on. Put in every single building that exists in that area, you know, the office buildings and the shopping centers and where houses where people live and so on. And put in demographic information about who lives in those houses, how many children they have, what kind of cars they drive, where do they work, where do they shop, where do their children go to school, and so on. All of the things that impact the way people use the road transport system to go from one place to another within that metropolitan area. And the idea was to have an electronic copy of the entire town, if you like, of Albuquerque, New Mexico, and so that you could study questions about road transport and how traffic flows in the system. You know, the idea to have a laboratory for doing experiments with the Albuquerque road transport network.
It's fascinating. It's really fascinating. And when you went to Intel, what kind of things did the engineers ask you about? What did you talk about there?
Well, I talked about computer simulation, and we talked, I mean, they do a lot of simulation there as well, in the kinds of simulating chips and the hardware aspects of how, the electronic aspects of how these chips work and so on. So we had some discussion about these kind of matters.
The computer programs like SimCity that you might have on your PC, how are those different, I guess? Are they different in kind or just sort of degree from the kind of simulations that you do?
Well, I think that, you know, if you take a game, or not a game exactly, but a simulation like SimAnt or SimCity, whatever, I mean, the designers of these games, in this case Nexus Corporation, they have a very difficult problem that they're facing because they have to create something that is sort of fun to play, which generally speaking also means they have to create something that has a lot of, you know, nifty graphics and that will still run on relatively mediocre kinds of computing equipment, like the kind of computers that we have in our homes. This is, and anybody who's actually ever done any computer programming and realizes that by far the biggest share of the resources in any computational effort is devoted to creating the pictures that you see on your screen, creating the graphics. And most of these games, then, they have dramatic simplifications in the actual rules about what the objects actually do as they're moving around in the city, because they can't devote very much computational resource to actually doing the simulation. They have to devote almost all of the resources of your PC to creating the pictures that you see on the screen. So they do a remarkably good job in these simplified rules. So it's the spirit of something like SimCity is exactly in the same spirit as the kind of simulation I just described of the Albuquerque road transport network. It's just that the degree of resolution is so much finer when you don't devote all of your efforts to creating graphics, and when you have something like a Connection Machine 5 to run the program on, and not just a, even something like a Sun workstation.
Right. Is there anything that is unsimulatable?
Well, that's a good question. I mean, it's bound up with the ideas of uncomputability. And we certainly know that with the kinds of computers we have today, that there are uncomputable quantities, but those quantities can be rather closely approximated by things that can be computed, and for practical purposes, uncomputability is not a very serious barrier.
And maybe you could explain a little bit about this, I'm curious, about quantum computing. Maybe you could explain a little bit what it is and how is it so much different that it will allow you to do some things that maybe now are unsimulatable?
Well, I mean, I'm not an expert in this area, so I'm not going to say very much about it.
Okay.
But I do know that, the basic principle of quantum computing is that in a quantum system, like I showed you earlier, this cat inside the box, that quantum theory allows for such objects to be in several different states at the same time, simultaneously. That cat can be alive and dead simultaneously. Classical logic only says that it can be in a single state at any given time. It's either alive or dead. Now, if you take advantage of this quantum phenomena that a system can be in several states at once, you can use this as a way of actually carrying out many computations simultaneously. It's a highly parallel way of carrying out computations. And it is known that there now are certain problems that are hard problems computationally with the kinds of computers that we normally use. They're what are called NP-complete problems, like factoring large numbers into their component pieces, that with a quantum computer, there are algorithms to do it that make the problem easy. So, for example, if you had a genuine quantum computer, most of the methods that people use today for cryptography, for encrypting data, these methods would all disappear because it would be easy to break these codes if you had a quantum computer. But the quantum computer itself generates all possibilities for a whole new classes of codes based on quantum effects that would and then restore the confidentiality of the data.
Do you think the concept of undecidability maybe is given a bad rap? That there's an overemphasis on proof and evidence that maybe we should just accept a few things that are undecidable like we do in our daily lives, and that...
Well, it's, as I said in my talk, it's a kind of mathematical notion. And in fact, if you don't have some notion of the infinite somewhere in the picture, then you never get notions of undecidability. It's intimately bound up with the idea of infinity. And of course, one might say in the real world of real physical objects and real human beings and real activities and so on, there's no such thing as the infinite. And so I think that it's a bit of a red herring as far as everyday life is concerned, because even our brains, you only have a finite number of neurons, and they can only be in a finite number of states, and you can only process information in with finite speed and so on. I mean, the real world is filled with finiteness. The world of mathematical objects is filled with the infinite, and undecidability is a consequence of the infinite, not the finite.
I'm just going to ask a few more questions. If people want to go to the microphones, I'll call on you in a second. You mentioned something about some restrictions on scientific research. Do you think there should be any ethical restrictions on scientific research?
Well, I think that certainly scientists have a certain measure of responsibility for looking at the, say, broader implications of some of the kind of work that they do, and that they should at least bring to the attention of the public at large what they might see as potential ethical conflicts or moral conflicts in their work. Now, I think that whether one should actually impose ethical restrictions or not, I mean, that's really a kind of, it's a kind of value that different societies will have to decide. They have to sort out, where do you put the mark, which you don't want to go beyond. And it's not really, in my opinion, it's not just up to the scientist to set that mark. I think it's up to the scientist to make the culture that they live in, the social group that they're a part of, aware of some of the possible implications of their work. And as concerned citizens, of course, the scientists may participate in the process, the political process, let's say, of deciding where the ethical limits might be. But I don't think that that's something for the scientists themselves to just unilaterally decide.
Sure. Do you have, just out of curiosity, do you have an opinion on cloning of humans?
I have an opinion, but it's not since it's not a professional opinion, I'm not a biologist, I'll reserve it.
Okay, that's fair. Okay, go ahead.
Yeah, I guess I have a two-part question. The first was, you speak often of the real world as distinct from that wherein people do their mathematical thinking.
Yeah.
And I'm wondering if you regard this in any way as something that requires justification or a double take, perhaps. It sounds like kind of a metaphysical first move, a cultural thing, where you take the real world and sort of put it out there as distinct from any mental process. And it seems if your mathematical world has these certain properties, that you just have to accept that's part of the physical world, being that there is just one world, and the division into this physical and non-physical seems rather arbitrary. The other question I had is probably related. You talked about Newton's law and the square of the distance between the planets and so forth, and you could imagine a culture where second power of something is always symbolized with a triangle, grows and shrinks at second power rate. It never occurs to them to use squares for that purpose of modeling second power. So when you say it's a fact of nature that Newton's law is obeyed, and then you state it and you use the word square, something cultural has gotten into that. It's not really wrong in any way, but it's arbitrary again. And I'm wondering if, in your view, can mathematics move in a direction that, like the astrology of old, gradually renders the current mathematics less and less intelligible to, at some point, they look back and they really can't read our math books and make sense of them? Do you think that's a possible outcome, even within one species?
Okay, before I answer either of those questions, I'd like to ask all future questioners to confine themselves to just a single question. I have a hard time keeping serial questions in mind, including these two. But in fact, I already sort of, let me address the second question first, the issue of the inverse square law. Maybe what I meant by the inverse square law is not a geometrical square. It means that things vary with the inverse of the second power of the distance between the planets. So the inverse square law means the exponent in that relationship is 2. It's not 2.5 or 3 or the square root of pi or any other number other than 2. So it's not like there's some triangles or some other geometrical objects. It's not a square in that sense. And as to whether in some future culture people will find our current mathematical books unintelligible, I think that certainly the symbolism that we use to express mathematical objects is rather arbitrary. It has a kind of historical origin, and one could easily imagine cultures, even on this planet, let alone other parts of the universe, that would use completely different kinds of symbols. But I certainly will be happy to make the distinction, and stick by it, between what I call the real world, the world of tangible material objects, chairs and tables and projectors and whatever, and the world of mathematical objects, the worlds of triangles and the worlds of integrals and the worlds of the kinds of symbols, the mental constructs that we use and assemble and operate with in mathematics. It's a very unclear issue as to where, if anywhere, these kinds of notions actually reside. I mean, there's one, it's part of the philosophy of mathematics to actually address the questions of the reality of mathematical symbols. And certainly one of the most prevailing views most mathematicians hold, people like Gödel or Roger Penrose, for example, is that these mathematical objects reside in some realm beyond space and time, in some Platonic realm, in a realm of ideal forms, and that mathematical relationships like the Pythagorean theorem about the length of the sides of a triangle, that these mathematical relationships are eternal, that they exist independent of the human mind, they exist in some realm. We as mathematicians are like explorers, and we go out and discover these relationships. There's another school of thought in the philosophy of mathematics that says, no, we're not discoverers at all, we're inventors. that the human mind creates these relationships and gives these symbols content and meaning, and that if there were no humans around, the mathematics would not exist. Well, for my own taste, I don't know which, nobody knows, of course, which of these are correct. As a mathematician myself, I'm rather partial to the Platonic view that we are discoverers, not creators, of relationships that exist in some realm beyond space and time. The real world is the realm of space and time and real objects. And I'm perfectly comfortable with that distinction. Others may not be.
Thank you.
Go ahead.
Hi. I work with very young elementary-aged mathematicians, and usually our problems end in convince me or prove your answer, explain your work. Often I get the answer, I just know it. I just know that this is right. And at first I was writing that off as they're being lazy or they just didn't feel like working it out. But more recently I've come to appreciate or look deeper at their actually telling me that. I was wondering, in the beginning of your lecture, you mentioned intuition. I was wondering if you could speak a little bit more about that.
About intuition? Yeah, I wish I could speak more about it, but I don't know too much about intuition. I have, I think we all, at one time or another, sort of experience sort of intuitive flashes of insight or whatever. And in fact, many of the mathematicians who believe in a kind of Platonic world, like I said a moment ago, take Gödel, for example, who developed this famous incompleteness theorem. Gödel's view of doing mathematics was that he would go into his office at the Institute for Advanced Study in Princeton, and he would close all the curtains in his office, and he would lay down on a kind of nice sofa there, and he would just close his eyes and somehow think. And what people would ask him, well, what is it that you're actually doing when you're, because he wasn't sleeping. I mean, he was doing mathematics, presumably. And what he said was this was his way of making contact with this Platonic realm, of somehow his brain would somehow plug into this Platonic realm, and he would actually see these relationships that then essentially he would just write down, in effect. And people would ask him, they'd say, well, how do you know that these relationships are true? And his answer was mathematical intuition. Mathematical intuition. And this is something that is very difficult to generate. Maybe you have a certain intuition to start with, and you can strengthen it by training and by experience. You know, just like you strengthen your body by going into the gym and working out with weights and whatever. Well, you can do the same thing mentally as well, I suspect, and help develop your intuition. But beyond that, I mean, I don't have any deeper insights to offer to you about that question.
Thanks for the question. Go ahead.
Yeah, we're talking a lot about discovery and the methods of discovery. A large number of the examples you've used here have to do with computational power, calculating all of the possibilities, all of the interactions given those rules that we have, such as the protein folding, knowing all the energy levels there. Could you comment on thoughts perhaps with dynamic systems, or where instead of having a robot having a huge set of rules of how to operate a leg, you have a very small set of instructions of when 3 are down, 1 is up, and a very small set, and all of a sudden this robot walks. Could you explain, or any comments on how that may fit into your thoughts on scientific discovery?
Well, I don't know about scientific discovery per se, but certainly my thoughts about the creation of a scientific answer to a question is completely bound up with the idea of computation. I said earlier, just think about a computer program. Think about the process of a scientific rule as being a computer program. And I think that the limits to what it is that we can possibly know in a scientific sense is completely tied up with the limits of our ability to actually carry out computations. And carrying out a computation of a scientific rule is basically following a rule, a program, or if you have a formula like Newton's second law of motion, or the inverse square law of gravitation, or Schrodinger equation, it might also be thought of as a rule. And of course, you might have, for a given kind of activity, like a robot walking, you may have a situation where you have a whole collection of different rules, and it might turn out that it's possible to find a much simpler rule that performs the same function. I mean, that happens all the time in mathematics. You have some very complicated, unwieldy model of something, and some cleverer person comes along and says, look, if you look at it this way and introduce this variable and so on, this 75-dimensional system you can get all the same behavior in a two-dimensional system. And so you have a much simpler rule that generates the same behavior. That's not at all uncommon. So I think that, though, as far as the practice of science is concerned, that if you depart from the idea of creating a set of rules for answering the question, then you will. That doesn't mean that you won't be able to answer the question, but you won't be doing science.
Thanks for the question.
Thanks.
I'm going to interrupt 1 second and ask one of my own, because I think it relates to what a few people have been asking. Can you describe for us your concept of emergence? I'm reading John Holland's book. And
Emergence.
Emergence.
The way that I think of it is that you have, let's say, a collection of objects, whether they're traders in a financial market or cars in a road traffic system, and these objects taken individually have certain kinds of properties. Cars have certain velocities they can travel at, or there's certain kinds of things that they do. But when you put these objects into interaction, you can see completely new properties emerge from this collective system that you could never see in any of the individual objects themselves. I mean, simple examples are like, take some nitric acid and a bottle of glycerin. Well, each of those objects taken by themselves, you can shake them forever and nothing interesting is going to happen. But as soon as you mix them together into nitroglycerin, if you just shake it a little bit, you might get some pretty interesting, explosive kinds of behaviors. So some new property has actually come about because of the interaction. Namely, all of a sudden you have a compound that is now highly explosive. Similar things happen, say, if you take some molecules of hydrogen and oxygen. Taken separately, these two elements are gases, very reactive gases. And you put them together, then all of a sudden you get a new object that has properties completely different from either of the component pieces. You have an object that's a liquid, namely water, and something that won't burn at all, just the opposite of something that will burn. So you see the same thing in these complex systems I've talked about. Think about cars moving around in a road traffic system. The interaction of these vehicles is what causes congestion, road traffic congestion. A single car doesn't have congestion. It's only a collection of cars in interaction that generates traffic jams.
I guess one thing I'm interested in is there are also maybe more social things that socially emergent properties, like democracy, or you take individual neurons and consciousness is said to emerge out of it.
Yeah.
Do you think those are similar types of emergent properties? And
fundamentally, yes.
And I guess one of the goals of John Holland and some other researchers at the Santa Fe Institute is to find some sort of theories or laws that apply to all emergent properties. Do you think they'll ever be successful?
Well, that's a different kind of question. Certainly all of us at the Santa Fe Institute have a kind of shared belief that if you take these complex adaptive systems of everyday life and sort of strip away the surface features that makes a system a national economy or a traffic network or something else, that there still remains a kind of distilled essence of complexness and in the abstract system itself, and that these systems have certain laws and rules that all their own, which generate complex behavior. And of course, part of our mission is to try and understand what are those rules and laws. And certainly emergence is a very, very important and powerful aspect of all of these kinds of systems. So it's a kind of, I don't know whether I would call it a law exactly, but it's certainly one of the most characteristic features of every complex adaptive system is that they do display emergent properties.
Thank you. You're out there. Go ahead.
Thank you. Before I ask my real question, I have kind of a sort of a point of information.
State your point.
I was wondering if you were familiar with a program that was originally generated at Apple called Coco. It's an environmental it's not an environment, it's a simulation environment designed for children. And they dropped the project, and another company named Cast has picked it up, and I forget their new name for it. But at stagecast.com, you can download for both PC and Macintosh now. If anybody out here has seen it and knows the new name, have you seen that?
No, I haven't.
On the stagecast.com, you can look it up. It's a really wonderful thing where children can create simulations, and definitely not as powerful as yours, but a step in the direction. My question is that I'm trying to work my way through Penrose's book, and Gödel's theorem for an amateur is not trivial. And one of the things that has struck me is there seems to be reflexive or self-reflexive element to that. And in that, the proof relies on some way. The sticking point always seems to be that it's trying to prove something about itself. And I wonder if maybe I haven't gotten far enough through it, or perhaps you could just comment on that. Unfortunately, my understanding is not to the level yet that I can say it's exactly here and kind of reiterate the proof for everybody. But maybe you understand where I'm going, or where I'm having trouble.
Well, certainly, Gödel's theorem always has some kind of self-referential aspect to it. I mean, the way that he proved it originally was to develop a very clever scheme by which he could code using numbers every kind of proposition that you could make about numbers. So he kind of cleverly figured out a way to get numbers, arithmetic, to talk about itself. And it's a kind of analog of these kind of sentences that you see in everyday language, like, this sentence is false. Okay, so that's a perfectly decent grammatical sentence in English, but it's a sentence that's saying something about itself. Okay, and this is a crucial feature of the proof of Gödel's theorem. There's a self-referential aspect to it. Yes.
And does this have create any problems if you're trying to generalize that? I mean, if this self-referential is the crux of it, well, maybe the statements just aren't true when it's self-referential, but when you're talking about something else, then maybe Gödel's theorem doesn't really apply.
Well, there are a lot of places where it doesn't apply. I told you that you have to have you have to be working within a logical framework that's consistent.
Right.
And if you go outside of that framework to, like, human beings or the human mind, which is, I think, manifestly inconsistent, because we're all capable of doing completely mutually contradictory things, or holding in our mind at the same time completely mutually contradicting views. I don't think Penrose's argument based on Gödel's theorem is much of an argument at all. For let's say he uses it to try and argue that it's not possible to build a computing machine that would think like a human.
Right.
Now, one of the things, if you want a nice, simple, compact version of Gödel's theorem, just think about the fact that when I showed you this picture earlier and I told you that there must necessarily exist always an undecidable statement, that not only is that statement undecidable, by jumping outside the system, you can actually see that that statement actually has to be true. It actually has to be true. You just can't prove that it's true using the rules of that logical system. And one way that I like to think about Gödel's theorem is just the statement that truth is always bigger than proof. Truth is bigger than proof. There always have to exist things that we know are true that we can never prove.
Seems like that could be misused too.
Well,
Thank you.
you have to keep the context in mind.
We'll take 2 more questions. Go ahead.
Excuse me, could you take a question from the balcony?
Yes, thank you.
Yeah, sorry. Us cheapskates up here.
I looked up there at the beginning and I didn't see anybody. Go ahead.
Thank you for coming to Portland. I found your last couple of slides very interesting on your latest thesis, say, of omniscience or potential omniscience for humans. Because of, and the thesis is that the world is somehow more understandable or tractable than mathematics is. That's very interesting to me. It seems like, however, that it's not enough just to have, say, causality to ensure that the world does have this nice property. For example, say a physical microcomputer is very much a causal system. Everything that happens in there does happen for a cause, or at least that's what we hope when we try to debug them. However, nevertheless, the halting theorem does apply to it. We've set up, you have a physical thing, a physical box here, which is doing physical manipulations in the real world, and nevertheless, it still is impossible for us to predict whether or not it's going to halt or not. So it seems like you'll have to add more theses than just the 2 that you had in your slide there. And I was just wondering how you're planning on elaborating this or proving it, or is it something that could even be proven?
Yeah, good. One of the pictures I didn't show you sort of bears on that point. I mean, when one talks about the halting theorem, of course, you're talking about the computer as a purely logical device, as if you like, a mathematical gadget. And you're completely ignoring all of, let's say, the hardware aspects of it. The fact that it actually is an object that exists in what I've called the real world or the physical world. And maybe I'll actually show you this picture. It's easier than, one picture here is worth 1,000 words. Where is it? Not that one. Yeah. Here it is. So there actually are 3 worlds involved here. I talked today about the worlds, the so-called real world and the mathematical world, but the world that sort of sits on top of both of them, in my view, is the world of computation. And for exactly the reason that you just described. The computer is simultaneously an object that lives in the world of mathematics when it's actually executing its program, going through the instructions and carrying out the rules that are embodied in the program. But at the same time, it is a physical device, and it's subject to all of the caveats and all of the aspects of an actual real-world material device. It generates heat, and it makes mistakes with a certain predictable regularity. Sometimes it doesn't actually carry out the operation that it's supposed to do, and so on. And so, again, I said that you have to keep these worlds very much in mind when you study the question of limits to scientific knowledge. Or are you studying the mathematical picture of a particular situation, or are you studying the real situation itself? And this picture, I think, makes it clear that you also have to have the computer, it sort of somehow does double duty in this overall scheme of things. Whether or not that necessitates adding something to my last transparency, which was really asking the question, if in the world of mathematics you have these notions of consistency and completeness, what would be analogous notions in the world of real things? I don't think that picture needs to be changed at all.
But causality alone is enough to induce undecidable problems.
No, I said that certainly it's not. And in fact, it's definitely not. You need a notion of the infinite. And if you have a completely finite world, no matter how big the finiteness might be, finite is finite, and it's as far away from infinity as the number 1 or 2. I mean, and in order to get undecidable propositions, there must be a notion of the infinite somewhere in the picture.
Thank you. Our last question. Go ahead.
Thank you. I gather then that Schrodinger's cat could survive by thinking outside the box.
Yes, indeed.
But my question actually has to do with these complex models. I was curious as to which of these is probably the most intriguing to you. Why was it intriguing? And how do you go about validating a model?
Are you talking about the simulations?
Like the simulations, yes.
Yeah, well, I didn't speak much about that tonight. Maybe you were at one of my other talks and heard me say more about it. But, you know, I can say always the one that's most interesting to me is usually the one that I'm working on at that moment. Because once you've actually somehow satisfied your curiosity and established the feasibility of actually simulating a stock market or the insurance industry or a supermarket, I mean, I've done all of these things. Then it becomes a little bit less interesting to just sort of further develop it. It's more interesting for applications point of view, you know, the continued development, because that's what basically, you know, pays the rent. But in fact, from an intellectual point of view, once you've satisfied your curiosity and you realize that it can be done and you've actually done it, then it becomes less appealing. But as far as the issue of validation, usually there are two things that you do, and they're both more in the realm of an art than a science. One is you basically look at the real system and see what kind of observations and data that you have from the behavior of the real system, and ask, does this electronic copy of the real system in your computer, does it generate data and observations that are look like they're from the same family as the real system? They don't have to be exact matches. I mean, that would be asking for way too much. But they have to look right. And the second thing, and maybe even more importantly, is that you bring in expert witnesses, essentially. You know, if you're studying a road traffic system, like in the Albuquerque situation, you bring in a bunch of people who have spent their lives working with that system, road traffic engineers and urban planners and so on. You set them down in front of the computers and you say, okay, here's the general situation. You know, we've got this these cars in these locations, and we have this kind of housing developments here and these bridges there and so on. What do you think is going to happen? Well, they make various guesses. There will be congestion here, or there'll be some problem somewhere else. You turn the system on, and usually what they see on the screen is not what they predicted. But then they say, oh yes, now I see, you know, it didn't happen the way I thought it would happen, but I know why it didn't happen that way. It's because of this or some other thing that they had perhaps neglected. But the fact is that they have a feel for the system, and they can basically say, ah, yes, you know, this looks right, it feels right again. And it really relies upon expert judgment and experience. Those are the two main ways of validating these kind of simulations, like any mathematical model, actually.
Thank you.
Dr. Casti, thank you very much.
Okay.
And have a wonderful wedding.
Thanks.